So, well, yeah, I won't repeat. I think it's obvious what to say. So, first of all, Bergeron and Gagnon introduced in a recent paper the excellence quotient of the Breuer order, which is mapping from permutations to non-crossing partitions. To define it, you consider position of exceedances, values of exceedances, and for each value which is not the value of an exceedance, you put an outgoing arc. For each value which is not a position of an exceedance, you put a no ingoing arc. And then there is a unique non-crossing partitions such that when connecting the arcs, that can be obtained by connecting the arcs. So for example, here I start with this permutation. Exceedances are the 1, 5, 7, 6, 9. And I put an outgoing edge on position 2, 3, 2, 3, 4, and 8, and ingoing arc at position 3, 5, 7, and 9, and connect to obtain a non-crossing partition. And they proved that the equivalence classes of non-permutation corresponding to the same non-crossing partitions form intervals of the Breuer order. For example, here we have the Breuer order of size 4 with the corresponding non-crossing partitions and the equivalent classes with red edges. And when you take the induced order on these equivalent classes, which is the same thing as taking the induced order on maximal elements, you get a lattice on the lattice isomorphic to the lattice of Dick passes, also known as the Stanley lattice, which is a little bit surprising because we started with the Breuer order, which is just a poset. And yeah, it's a Dick passes order. One Dick pass is below the other if it stays below it. It's the natural order of Dick passes thing. And I'm saying that we started with the Breuer order, which is just a poset, and we obtain like a quotient, which is a distributive lattice. It's a much stronger property. It's a little bit surprising. And in fact, this can be explained by the fact that the exceedance quotient is induced by a lattice quotient of the ASM lattice. So now we have a mapping from ASMs to Dick passes, which can be easily obtained by looking at the height functions of the ASMs. Height functions are these matrices in the middle that are very similar to the corner sums. And when you take the main diagonal and the diagonal just above, the values give the height of a Dick pass. Yeah, okay, that's nice. But what Bergeron and Gagnon used their excellent quotient for was finding to construct basis of the Temperley Lieb algebra. So I will explain a little bit what's the Temperley Lieb algebra. So usually it's constructed by composing non-crossing arc diagrams. So you take two diagrams, you glue them together, you simplify the loops, and then each disconnected loop multiply the result by a parameter Q. And here we consider the Temperley Lieb algebra with parameter Q equal to 2. And this algebra, it is isomorphic to the following quotient of the algebra of the symmetry group by this linear combination of permutations of length 3 by the generated ideal. And they prove that when you take exactly one permutation in each equivalence class of the exceedance quotient, you embed these permutations in this quotient, you get a basis of the Temperley Lieb algebra. But it turns out this is a more general phenomenon. We consider any quotient of the SM lattice isomorphic to the Stanley lattice. And when you take one permutation in each congruence class, these permutations form again a basis of the Temperley algebra. We have also these nice properties, like in each congruence class, there is one minimal permutation which avoids the pattern 3 to 1. The maximal elements of each congruence class is a covexillary permutation, which means it avoids the pattern 3, 4, 1, 2. And so for an example, I drew the SM lattice of size 4. I just had to zoom a little bit because it was too big. And I take a quotient isomorphic to the Stanley lattice, and as you can see, maximal elements of classes are permutations. Convex permutation. We do not see the permutation 3, 4, 1, 2, but it's not the maximal element of a congruence class. You have to trust me. And there is always a minimal permutation, avoiding 3 to 1. What? I was just random colors. Ah, no, for the SMs. Yes. Yeah, yeah, that's it. Red, it's ones. Blue cells are minus ones. White, it's zeros. Yeah, sorry for people that do not see colors. It's a little bit a mess. So I won't talk so much about the results, but rather about the tools that you use to obtain these results, because I find them somehow more interesting. So first of all, we need some basic properties of distributive lattices. So we already talked about the Birkhoff representation theorem, which states that all distributive lattices are isomorphic to the lower sets of a poset ordered by inclusion. The corresponding poset can be obtained by taking the poset of joint irreducible elements of the lattice. So for example, here on the left, we have a lattice, a distributive lattice. Joint irreducible elements are the one with just one element below. So here it's A, AC, AB, ABD. And the induced poset, when you take the lattice of lower sets, you get back the distributive lattice. So you have like a bijection between distributive lattices and posets, which is very useful because a lot of properties of distributive lattices translate nicely on the posets. For example, the lattice congruences of distributive lattices, they correspond to subposets of the poset. Here we have a quotient isomorphic to a Boolean lattice, and the corresponding subposet is an anti-chain, which makes sense because lower sets of an anti-chain form a Boolean lattice. Yeah. And when you look at the poset of irreducible elements of the SM lattice and the Stanley lattice, they have very nice geometric structures. If the SM lattice, it's a tetrahedron. For the Stanley lattice, it's a triangle. I will explain later what this coordinate means. And we had to use a lot of this three-dimensional structure. For example, here we represent an SM as the boundary between the lower set and its complement in the poset. And we're a little bit surprised by the result. It looks nice, but also you can get back the ISM from the vertical projection just by looking at points where there are 4 colors around them. If it's in one direction, you put a 1, in the other direction, you put a -1. From this projection, you can get all the ISM-related objects, such as 6 vertex configurations, Felipak loops. There are also these ones on the right below, which are like dual Felipak loops. I don't think these objects are already known. Those are nice. Yeah. And also, if you look at the drawing, and if you look at this drawing, the rhombi I put in for the boundary, they make like rhombic dodecahedra. So this gave us the idea to represent ISM. I know the other to represent ISM. Okay, to represent ISM as stackings of rhombic dodecahedra. Yeah, but yeah, I understood, but it's very confusing. Yeah. And so we printed this. It was very useful for first playing with the ISM, understand what's what's happening. And they also put like little strokes to obtain fully packed loops. But before that, we were playing with juggling balls because seen from above, it looks like the rhombic dodecahedral also. Yeah. And now, if you remember what I was saying before, we are interested into questions of the ISM lattice isomorphic to the Stanley lattice. And this corresponds to finding superset of the tetrahedron that are isomorphic to a triangular superset. And it's very constrained. There is not a lot of ways in which we can put a triangle inside this tetrahedron. I'll explain. But to encode like this triangular superset, you just have to remember at which depth it is when you see it from the side, like for horizontal projection. And these depths, we encode them with a Gelfand settling triangle, which we call Catalan triangles. So it's Catalan with a lowercase c because we were in Barcelona when working on this project. And the Catalan triangles, these are exactly the Gelfand settling triangles with bottom row 1, 2, 3 up to n, which are gapless on columns and diagonals. And gapless, it means that entries increase by at most 1. So n quotient of the ISM lattice isomorphic to the Stanley lattice, these are in bijection with Catalan triangles. Uh, like column and diagonals play symmetric roles. And, for example, the excellence quotient, it corresponds to this superset, which is like undulating in the tetrahedron. And if you look at the values of the triangle, they're also undulating somehow. And these Catalan triangles, they're, I think, interesting objects by themselves. For example, they are in bijection with two colored pipe dreams. These are triangular pipe dreams colored with two colors. And on bumps, you cannot have the same color. And the bijection is very simple. Is in one direction, you put a red stroke if the values are different. And in the other direction, you put a red stroke if if the values are equal. And with this, we obtain like this equation, which reminds a little bit from the two animation of ASMs. It can be proved easily, but it would be nice to have a combinatorial interpretation of this. BCC is just the number of bicolored crossings. And these Catalan triangles, you can also order them coordinate-wise, and you get a distributive lattice, which is very similar to the lattice of alternating sign matrices and the Stanley lattice. So here it's lattice on the left, it's the lattice of Catalan triangles of size 4. And on the right, you have the poset of joint irreducible elements. And I'll explain why this lattice looks similar to the ISM1. So the construction I talked a little bit about yesterday is the following. You start with a small poset P. Then you consider the tuples of elements of P up to permutation. And there is the natural order on these elements, which is one tuple up to permutation is below another if there is one permutation for which they are one below the other coordinate-wise. And these tuples up to permutation, you can encode them just by taking the multiplicities. You count how many times an element appear in the tuple. And we call these vectors barycentric coordinates. And the order of the poset translates nicely on these barycentric coordinates. You just have to consider inequalities between sums on its upper sets of the poset P. And for example, I talked about the SM lattice, the Stanley lattice, and the Catalan triangles lattice. Their irreducible posets can be obtained by doing this construction with this poset. The SM lattice, you can obtain it with like a butterfly poset. The Stanley lattice with this one, and the Catalan triangles with a diamond. But there are a lot more examples of this construction. For example, with a hook, you obtain Magog triangles. With this one, gapless Gog and gapless Magog triangles, which are isomorphic lattices. You can also obtain Gelfand-Settling triangles with top row 1, 2, 3, up to n. But there are other examples in higher dimension. For example, you can do totally symmetric partitions in any dimension, and also subpartitions of stair-shaped partitions, which is a generalization of Catalan numbers. So, and yeah, the open problem I talked about yesterday, it was about the enumeration of some of these objects, for example, gapless triangles, the Catalan triangles also. No. So, oh. Thank you.